talk about our work on non-impulsive contact-implicit motion planning for morpho-functional loco-manipulation. My name is Adar Salagame. I'm a PhD student with Northeastern University at the Silicon Synapse Lab. And on this work, I worked with Dr. Eric Sihite, who's a postdoc at Caltech, Kritika Gangaraju, and Harin Kumar Nalaguntla, who are MS robotics students at Northeastern University, and Dr. Schoner and Dr. Ramazani, who are professors with the Department of Electrical and Computer Engineering at Northeastern. This work is based on our snake robot COBRA, which is a multimodal slithering snake robot. COBRA consists of 11 single degree of freedom actuated joints and 12 links. Each of the 12 links are independently powered with their own battery, and all 11 joints are daisy chained through an RS-485 bus that is controlled centrally at the head. The joints are arranged such that successive joints are at 90 degrees to each other. So you have a yawing joint followed by a pitching, followed by a yawing, and so on. COBRA is a multimodal robot, which means it has different kinds of locomotion gaits that it can achieve, including a standard snake-like gait called sidewinding, and also several tumbling and rolling gaits. One of the features of COBRA and most snake robots is that their means of locomotion is extremely contact-rich. So at all points of time, especially with gates such as the sidewinding gate, the robot is making contact with the ground at uh, over 3 to 4, or sometimes all links simultaneously. And using this contact-rich nature of its gate, it's able to generate required moment and force about the center of mass to move the robot forward. So what we want to do with this work is use the contact-rich nature of COBRA's locomotion to manipulate an object and move it along a desired path. So as shown in the diagram here, in this case, we consider a box that is placed in front of the robot. And we have some desired path that we would like to move this box along. And we would like to figure out the joint angles and joint trajectories required to move the box along this path. In order to do this, the approach we take is implicitly considering the contact forces with both the robot and the ground, and also the robot with the box, and incorporate all of this dynamics into a unified model that we can apply optimization on to develop a desired path. Here's the dynamic model of COBRA. M here is the mass matrix. U is the input vectors, which is the joint position and velocity. Um, H is the Coriolis gravity and actuation terms. And this is a function of the external forces and their Jacobians. Through the normal cone inclusion concept, we can define constraints for the contacting points on the robot that say that the contact forces, F external, must be within a normal cone. And we define a gap function, which is the distance between the outermost point on the robot and the ground, and the robot and the object. Dynamics as follows. So the rate of change of this gap is a function of the contact Jacobian and the joint inputs. So this can be simplified into this equation where this term represents the de Lass's matrix, which is the apparent inverse inertia at the contact points. And C is the terms that are independent of the external forces. So from this, we can write this optimization problem that minimizes the total external forces subject to the constraints of the robot dynamics and the joint position and torque limits. Using the Simulink multi-body toolbox. At the center here is the COBRA model, which is a high fidelity model which incorporates the full shape and configuration of COBRA, including all the outer geometries and the inertia properties. This interacts with the ground plane and the box through a contact model that is defined based on a smooth spring damper system, um, which gives out contact locations and uh, reaction forces for both interactions between the robot and the ground plane, the robot and the box, and between the box and the ground plane. We have a gate generator that generates joint angles that move the robot around um, based on some predefined gates. And using this, we uh, push the box uh, using different gates and study the effect of ground reaction forces. All the different tests that we did using the simulation. Um, the top two are lateral rolling gates where it holds a C shape and an S shape. This lets us place the contact points with respect to the box in different locations, changing the overall contact forces. And also at the bottom left, you see the J-shape gate, which is asymmetrical, and this lets us actually change the direction of pushing of the box. And finally, we also test this with the sidewinding gate. And the purpose of running these tests is to understand uh, how the ground reaction forces and the contact locations look like. These are things that we cannot study on the real robot. Um, and because of that, uh, we need to do this through simulation. Locations and contact forces for all the previous gates. This is the C gate, which shows a periodic contact for every link. In this gate, in all of these lateral rolling gates, every link is in contact with the ground at all points of time, which produces an interesting ground reaction force profile. Whereas with sidewinding, you have intermittent contacts, and therefore the ground reaction forces are more sparse. We can also study the joint torque profiles during this test. So shown here is the torque profile for two of the um, joints, one pitching and one yawing, for each of these different gates. Through this, we compare the total work done by each of the gates and the power consumed during each of these tests. So we calculate the work as the total sum of the torque required by the joints multiplied by the joint angle moved. And so this is the work done by the robot, and the work done on the box as the total contact forces on the box multiplied by the distance moved by the box. And what we want to see ideally from a good um, loco-manipulation gate is that the work done by the robot is minimal while the work done on the box is maximal. So this S-shape lateral rolling gate appears to show the highest efficiency with this regard. And you can see the same thing with the power comparison, which is a function of time. And you can see that the S-shaped lateral rolling gate appears to be the most power efficient. So what we get out of this work is an optimization-based framework that uh, incorporates contact-implicit uh, non-impulsive contacts for motion planning, and it shows a high-fidelity simulation that helps us track contact locations and ground reaction forces. So using the simulation, we can build a model uh, that we can validate and um, test the controls for. So the next step will be to implement this motion planning framework using contact sensing data, first with simulation, and then eventually on the real hardware. This work was funded by NASA's Innovative Advanced Concepts Program. Um, and thank you for your attention.